Okay, so good morning. Today I brought some kind of metal fasteners so you can see and touch directly them by hand. So I will just pass now to you. If you remember, we showed a couple of days ago this kind of connection here. A metal plate that is attached on one side of the beam. Then you have another metal plate attached with some screws on the other side of the beam. And then the two will be slotted inside in this way. Okay? So one side, the other side, and you just have, you get rid of this problem of bearing perpendicular to the grain. So as you can see, there are the holes already cut, drilled in an inclined direction, so 45 degrees. So the idea is that those plates will be connected to the timber member using screws at an angle to the grain, 45 degree, inclined screws. As I mentioned yesterday, I would say in these last years, more and more we are using inclined screws. Basically because we are using self-draining screws, which don't need, at least for this diameter, the pre-hole. So they are kind of, you can screw them inside and by losing not too much time, so it's very easy. And of course, this inclined direction ensures high stiffness and high strength. So we will see that if we put a screw, let's say at perpendicular to the shear plane, we can get high activity, but lower stiffness, lower strength. If you put the strength at an angle to the grain, 45 degrees, we get hardly any activity. So we don't get any significant activity, but we increase significantly the stiffness, or slip modulus as it is called, and the strength. So for this reason, very often we have this system where we put inside the screws at an angle to the grain. Basically, this is the idea. Something like this. Now, this probably is not the right screw, but at least you can see. So all of the screws are fixed in this way. Remember, on one side and the other side, of course, other screws on the other side, and then just open the screws. Okay? This, of course, these plates usually they are hidden inside the wood because the client usually doesn't like to see this steel work on the side. So usually it's hidden, it's concealed inside the wood. And of course, this is the same concept, but applied to a larger cross section. Same concept. So, again, the advantage of this, we don't have the limitation of the strength of wood perpendicular to the grain, which is quite low, remember. So we don't have this problem, and then for sure we have a better behavior. So if you want to touch, pass it around. So, yesterday we've been talking about nails. So this is the version, if you remember we said the nails can be smooth or can be ring shank nails, so not smooth. So this one is the version of the nail which is not smooth, ring shank nail. Of course the reason why we profile the nail in this way is to increase the friction. So of course it's not like a screw because as you can see there is not a thread here. But it's a kind of thread but it's not a spiral thread. Okay, it's not a thread. The thread should be spiral. This one is not a thread. Just to increase the friction. Of course a nail like this cannot be banged because you would need a huge weapon to do this kind of thing. But so you need to breathe to do a hole and then you put it inside. So by increasing the friction, of course, we increase the strength, mostly the withdrawal strength, so we can have a better behavior. We pass around also this. Okay, today we're going to talk about bolted connections. So, in terms of timber, the bolts are very similar to the bolts that we know. Actually, you don't know yet, but you're going to study steel construction. The main difference being the size of the washer. So this is a typical bolt for screw, for steel with a small washer. Consider that for timber the washer should be at least twice the dimension of this, because otherwise, when this one is going to bear on the surface, it will just punch it and will just go inside. So we need to have a much bigger washer like this. This, of course, this is a washer not for this. This bolt is a washer for a bigger, large diameter bolt. But as you can see, it's definitely larger compared to this. See the difference between the two. So the most important difference, as I said, is for timber. We need to use larger washers. Usually, when we purchase a bolt off the shelf, they sell bolts for steel, not bolts for timber. So we need to buy separately the washers, because in the bolts we will find a washer for steel, not for timber. So let's see a few words about bolted connections. We can make it work. Yeah. In the case of bolts, of course, the diameter is larger, so we need to drill a hole first. So we drill a hole in the timber, which means that we are going to break the fiber on the hole. And this means that in general, with the bolts, we are going to weaken the cross section of the timber. Because the bolt is not like the nail parts the fiber, but in this case, of course, we need to break the fiber. And so we are going to weaken the timber cross section. We have a general large diameter fastener, so more rigidity. The force are mostly transferred by bearing. There is also, if you remember, this rope effect, but it's not as large as in the case of screw. So mostly by bearing. So if you want, by embedment, contact between the wood and the dowel and the shank of the bolt. In this case, we use a few large fasteners, which means that we have also a higher load per unit area, meaning that we might have more problems about splitting. All these kind of failures in the connection are more likely because we have higher stress concentration compared to nails. So for bolts, again, we have this formula to calculate the characteristic value of the yield moment. If you remember the discussion yesterday, this is a semi-empirical formulation that in the new generation of Eurocode 5 will be changed to have a more physical sense. So we will have a different coefficient times FUK times T to the power of 3, which is what should be there, not T to the power of 2.6. And then we have other semi-empirical formulas to calculate the characteristic embedment strength values. If you remember, when we calculate the shear strength in a connection with dowel type fastener, we need some variables. We need some geometrical variables like the diameter of the fastener and the thickness of the two timber members. And then we need some mechanical parameters. The mechanical parameters are the characteristic yield moment, which is calculated with this formula, the bolt, and the embedment strength. The embedment strength is calculated, again, you see, with this semi-empirical formulation, depending, in this case, depending on the angle of the force with respect to the grain. So now we have a new thing, new concept. For nail, we said yesterday, for nails, the embedment strength was independent of the angle of the force with respect to the grain. So it was the same thing in terms of embedment strength to have a nail which was pushed on the timber parallel to the grain or perpendicular to the grain. In this case, this is not. So in this case, you can see we have and FH0K, which is the characteristic embedment strength parallel to the grain, given by this semi-empirical formulation, depending on the diameter, and depending on the characteristic density of timber. And then we have another formulation based on the Hankinson relationship to calculate the embedment strength at an angle alpha to the grain. You see, as a function of the angle itself and as a function of FH0K, and also as a function of this K90 coefficient, which is different for softwoods, LVL, and hardwoods. Okay? So in this case, the design of the connection will be slightly more complex compared to the case of an A. Because if you remember, yesterday we said for the net, since the strength, the embedding strength is independent of the angle, we can go to do the direct check in the most stressed net, independently on the direction of the force. While instead here, since the strength, the embedment strength, depends also on the angle of the grain, theoretically we need to do the checking each bolt of our connection. Because it's not sure that the most stressed bolt will also be the, let's say, the critical one. You could have, for example, that the most stressed bolt is loaded parallel to the grain, where you have also the larger strength, and let's say a less stressed bolt is loaded perpendicular to the grain, where you have a less resistance. So it could be that the second one is more critical than the first. Okay? So with the bolt we need to be more careful. Theoretically we should do the check for each bolt, if of course if you have different directions of the forces, the shear forces acting on the bolt itself and on the connection. Here you can see the difference, the ratio between embedment strength at an angle to the grain and embedment strength parallel to the grain. So this decrease, we are talking about decrease up to 40%, is maximum, as you can see, for softwood. It's less important for hardwood, and it depends also on the diameter. For larger diameter, you have a larger increase. Just a reminder, as I said yesterday, the embedment strength is not the property of the wood alone. It's the property of the system, fastener, wood considered together. In fact, you can see that there is a dependency on the diameter. Okay? So it's a kind of system property. And this is what I was telling you before. You might have, for example, you see here, this is the bolt, which is the most stressed one. In this case, you see that, for example, with respect to the rafter, where the grain is running this direction, you have that this is the most stressed, and it is mostly stressed perpendicular to the grain. While instead, for example, this other one is less stressed, is stressed also parallel to the grain. So in this case, it's very likely that the critical bolt will be actually the bolt with the larger applied force, because this force is applied perpendicular to the grain. Okay? But there is another difficulty in this assessment. That you see, this bolt here is loaded perpendicular to the grain with respect to the rafter, but it's loaded mostly parallel to the grain with respect to the column. Actually, this was a different case. This was, if you remember, the case of the gas. So, if this plate here is made of steel, of course, what counts is only the rafter. But suppose that now we have a connection between a column running in this direction without the steel plate and the beam running in this direction here. When we calculate the strength of this bolt in the formula of Johansen, we need to put the embedment strength of both members. Of this member here running in this direction and the other member here running horizontally. So for one, the embedment strength of this member will be very high because the stress is mostly parallel to the grain. While instead the embedment strength of the rafter will be lower because the same direction is actually pointing towards 90 degrees to the grain. So the embedment strength here will be less. So in the formula we need to take into account both. Because if you remember the formula, we have the embedment strength of member 1 and the embedment strength of member 2. And then if you remember, there is a beta ratio between the two embedment strengths. So this, in a situation like this beta value would be very high because we have a difference significant. In one case we are almost perpendicular to the grain, the other case we are almost parallel to the grain. So we have this maximum difference of 30-40% between the two values. Okay? So remember, for the bolts, in general, strictly speaking, we should check the design inequality, this design inequality for all the bolts, because it's not sure that the most stress one is also the most critical. It's clear this? Okay. If we use plywood, we have another formula to calculate the embedment strength. In this case, also for the bolts, the embedment strength is independent of the direction of the shear force. Why is that? Because if you remember, plywood, it's a more isotropic material. So it has more or less the same properties in all directions. There is no reason why there should be a difference in the property in one or in the other direction. And then we have this minimum value of spacing and edge and end distances that we saw yesterday for nails. In this case, they are slightly different. For example, let's have a look to compare also to what we saw yesterday. So if you have a bolted connection like this, so if you remember, these distances here are given in order to ensure that all the brittle modes that are not covered by the Johansen equation won't occur in the reality. So this is the grain, this is A1, this is called A3T, and then we have A2, and A40. Suppose that the force of the bolt is parallel to the grain. So, from the table, A1 parallel to the grain shall be greater than or equal to 4 plus cos alpha times d. In our case, alpha is equal to 0 because we are loading parallel to the grain. So cos of 0 is 1. So is 5d. A2 greater than 4d. A3d so A3d greater than max between 7d and 8 millimeter, and A4t greater than max between 2 plus 2 sin alpha d and 3d. Now, if you compare now this with the value of yesterday about the nails, what can you see? I don't remember now by heart. If you just check the values that we wrote yesterday for nails, so A1 I think was more, no, A1 was more if I remember well. Also A2 was more. Try to check the value we wrote yesterday. What was A1 for a nail? How many diameters? 10D. So you see 5D is halfway. So the bolts are less critical. Then instead of A2, what was A2? 5D, today is 4D, slightly less. 83T, then we have 7D. Yesterday was 50, if I remember right. Was it? Yes, so there is half. And A4T, 3D, we have today 5D. So the nails are more critical compared to the bolts in terms of minimum distances. In any case, just remember that those values here for a still bolted connection would be lower. So this 5D would go down to 3D for steel connections. This 4D, I think, is 2D for steel connections. And this 7D would become 1.5 for a steel connection. Okay, so we are, anyway, for timber, the connection made of timber are more critical compared, in terms also of distances compared to the connection made of steel. Meaning that when we design a connection, or when we design a connection, the first thing, we need really to do a drawing to understand if if we will have enough room to put all our nails or fasteners for the connection. Because these distances are much higher compared to steel. This is important. Okay, so these connections are more bulky, I would say. They need more space compared to a steel connection when we talk about timber. So very often, the criterion that decides the size of the member is not actually the ultimate limit state or serviceability limit state of the member, but is the room needed for the connection that will have to connect this member to another member. So very often, the connection design governs the design also of the minimum size of the members. Okay? So, then we have this formula for the effective number of bolts. For one row of n bolts parallel to the grain direction, the load carrying capacity should be calculated using the effective number of bolts, where NEF is minimum between n and n to the power of 0.9 times A1 divided by 13D to the power of 0.25, 1 volt, which is 0.25. Okay? So in this case, as you can see, we have a continuous function which makes this effective number dependent upon the number of nails, the number 19, and you see the diameter and also the spacing of the nail. Okay? Now, suppose that you have to design a connection like this, subjected for the sake of simplicity only to shear. So the whole connection is going to transfer a shear force like this, axial shear force. Let's call it F. No, sorry, let's call it N. Okay? Now, suppose that this connection is done in this way here. I cancel here now. So looking down, it's done in this way. One member and two members. Okay, so we need to calculate the actual, we need to do the, if you want, the global verification to check if this connection is safe or not at ultimately mistake. Okay, so we know the force, the axial force demand and D, and we need to calculate, we need to check this connection against ultimately mistake. So how do we proceed? So we do this exercise together to see if everything is clear. How would you do it? This is now, it's not a design problem. This is a verification problem. Ultimately mistake. You know this connection, you want to check whether this connection is safe at ultimately mistake for this node MD. Okay? So how do we proceed? First of all, what we need to do? How do we do it? Let's start to get confident with this kind of problems because, as I said last time, the exam of this course will be a written exam, as you know from the last exam that you did with me. And this exam, you will have to design a member, like a timber member, for example, a beam or tie something. And then you usually have to design a small connection. It could be a design like this, for example. So how do we check the safety of this connection system? How would you do it first? I think we should start from the design inequality. What is the design inequality at the global level here? At alternative mistake, what do we need to write? So ND shall be what? What do I need to compare the design axial force of the connection with what? With? The resistance of what? It's correct. I need to compare this with the resistance. The design resistance of what? Of the whole connection, right? With the design resistance of the whole connection. So I will need to find out what is this design resistance of the whole connection. So, in our case, how can we calculate this design resistance of the whole connection?
I have multiplied for a single
What do you do? RD, so RD is equal to what? NF, what is NF?
number of fasteners.
Okay, so let's call it N. N is the number of fasteners. Okay.
And 100.
Okay. I see. N, but N over NF in this, maybe not in this design inequality, because this design inequality now we are looking at the global resistance. So the global resistance, what do I need to put? All the fasteners. So first of all, I will need to understand how many fasteners to put in the global resistance here. How many? If I calculate the total, the resultant, you need to put N or NEF. N. But this is tricky here because when I calculate the actual resistance, we said that if you have more fasteners than 9, the actual strength of those fasteners is not the number of fasteners times the strength of a single fastener, but it's lower. Is N EF times the number of fasteners. So here I should write the effective number of fastener times the strength of a single fastener. Strength of a single fastener, if you want to use the right symbol, now I can't remember by heart what was the right symbol, go back. You can say times F VRD, where FVRD is the design resistance in shear of a single fastener. Okay? Right? Okay. and EF is the effective number of fasteners that I can consider to take into account that we need to exclude splitting and other failure mode like that. Now, if you look at that, so FBRD, this one, is calculated with the usual format, K mod times FVRK divided by gamma n. Okay? Where FVRK is the characteristic shear strength of a single fastener calculated using the Eurocode 5 formula. Okay? You have some doubts? Okay. If you go back now to see the Johansen formula, they say that this is what you calculate from the Johansen equation is the characteristic shear resistance per shear plane per single fastener. Okay? So what we calculate this one from the Johansen equation is the shear strength per single fastener per shear plane. So what does it mean? What do we still miss here in this equation? If this is the strength per single fastener per shear plane.
Number of shear planes.
The number of shear planes. So what is the number of shear planes in our case? 2. It's clear for everyone. Why is it 2? Why is it 2? Because this comes from the fact that if you go to solve this bolt here under the pressure, so you would have something like this. Okay? So, what would be the shear? Well, I shouldn't do here, I should do here. Along the bolt. So what would be along the bolt? Let's try to sketch here along the bolt, along the shank of the bolt, the shear force diagram. If you have a distribution of forces like this, what would be the shear force diagram? What is the value of the shear here? This point. So what we are doing now is to solve a problem of statics. Given a beam like this, because the bolt, you can see the bolt as a beam having which kind of cross section? Where is the bolt that I gave you before? Okay, so this one is a beam having what kind of cross section? What is it? Circular, a circular cross section. So it's a beam with circular cross section. So this is a cross section loaded with this system of forces. Okay, and I want this system of forces in equilibrium. It must be in equilibrium. And I want to know now the shear force diagram. Can you help me to find out the shear force diagram? So, what is the value of the shear here? 0. Then you have a distributed load acting in this direction. So how is if you remember the shear, what is the relationship between the shear diagram and the load? There is a differential relationship between the shear and the load. And between the moment and the shear, the moment and the load. It's linear. Why is linear? Because the load, in this case, will be uniform, and the shear is the integral of the load. Or if you want, the load is the first derivative of the shear. Okay, so it will be linear. Now, there is a different convention on the side between you and me, but this doesn't matter because we said that the shear, we need to know the value, the absolute value of the shear. We don't care about the sign. So, I would basically write in this direction here. You would write in the opposite direction, but this doesn't matter. Okay? And then what's happened? Jump this way? This way. Are you sure? Jump this way? No. It changed direction, but it kept on being. Do I have a discontinuity here or not? So do I have something like this, or I move in another direction? Do I have a real jump there or not? This is my question. No. Why not? Do I have a jump? What should I have? Do I have a discontinuity? What kind of force should I have? So I have a concentrated load, but here we don't have any concentrated load. We have just distributed load. So from here would be linear. Okay? So if you have doubt from the opposite side, we'll go this way, because you see the forces are this way, so this, and here would be something like this. Okay? So this is the shear diagram in my boat. Okay? So you see that we have this bolt, mass transfer, a shear value here in this cross section and in this cross section. So we have two cross sections where the bolt has to transfer some shear. While instead, if I have a connection like this, here how would be the diagram? Very similar to what we just saw, just halfway. It would be something like this. Okay. So we have to remember that we have to count the number of shear planes, which means that the number of possible planes, well, I can have a slip between the different members making my connection. Here I have two planes. So here, like you said correctly before, I need to multiply this also by the number of shear planes, MS. Okay? Now, going back to our problem. So in our case, we say NS is equal to 2. Now we need to find out, in our case, NDF. How can we calculate NDF? Now we need to be careful, because NDF, if you read the regulation, we go back. For one row of n bolts parallel to the grain direction, we calculate NDF in this way. So this is the grain direction. In our case, we have how many bolts aligned in the same direction? In other words, NDF equal, we said minimum, n to the power of 0.9 times A1 divided by 13. So what is the number of n that I need to put inside here? You need to think about it a little bit. Because if you read the regulation, it says for one row of n bolts parallel to the grain direction. One row of n bolts. In our case, do we have one row of n bolts or we have something different?
rows.
We have 3 rows, in our case, of 3 bolts. So what does it mean? That in our case, the n to put inside here will be which number? If we have 3 rows of 3 bolts.
Times.
3?
Times.
What does it mean? 3 times? It's probably right, but
Multiply.
so, in our case, this NEF would be given by
3.
3, because we have 3 rows times, let's call this one, let's call this NF prime, just not to make any confusion. NF prime will be 3 times NEF, where n is equal to 3. Exactly. Okay? Perfect. So here we need to be careful not to do a mistake, just in order to put, since we have 9 bolts, one could say, okay, I put inside here 9. That would be wrong. Because in this formula we need to put n equal to 9 if you have 9 bolts on the same line. Instead we have 3 lines of 3 bolts. So it's perfect, we have to do it this way. Okay? So be careful about this, not to make this mistake. Okay? Then of course in this formula we need to measure A1 and we need to measure the diameter, and then we calculate here the value that we get. And then to conclude, we need to calculate this FVRK. To calculate FVRK, we go to the formula that we saw yesterday. We go here backwards. Is this our case? No. There's another one which is actually our case. This one. This is our case. So we need to calculate FH1K. So you see 1 is this member, the thinner member. This is member number 1. This is also member number 1. And this one is member number 2. We have to calculate FH1K, so the embedment strength of member 1, and FH2K of member 2. If you look at the formula that we saw before for FH1K, FH alpha for a bolt, we saw that this formula, in this case, the embedding strength depends upon the inclination of the shear force with respect to the brain. So in our case, which value of alpha do we need to put? In this case, what will be the value of alpha? Zero. So alpha equal to 0. So we will use it for both FH1K and FH2K. We will use alpha equal to 0, which means F. If I remember well, is written FH0K. You can check. One of the two formulas, I think one was FH0K, something similar. So we use this one. Then we need to calculate the MYRK, so the yield bending moment of the bolt. And then we need to calculate this beta, which is the ratio between FH2K and FH1K. In our case, this beta will be equal to 1, because we have same timber, the same direction, then this is equal to 1. Okay? Then you calculate, you will get 4 numbers here. Of these 4 numbers, for example, you take the first one is 10, then the second is 13, the third is 17, and the last one is 9. Which value do you take?
Lowest.
The lowest one, so the last one, so 9 kilonewton, and the lowest one will give you also the failure mode. So if it was the lowest one, you will get this kind of failure mode. Okay? In this case, in general, you don't care about the failure mode, just care about the load carrying capacity. But if instead you were in a seismic region, and this was your dissipative connection, then we will learn that we need also to care about the failure mode. Because if you are in a seismic region, we cannot accept, and this is a dissipative connection, so a connection that should be designed to dissipate the energy, like, if you remember, the beam, your reinforced concrete frame, you have to design the beam at the interface with the column in such a way to dissipate connection with the capacity design. In this case, if this is a similar connection, we will have to ensure that the failure mode it involves at least one plastic hinge in the metal fastener. So this is okay, but the other one wouldn't be okay. Okay, so it's clear what we have done so far. Now we go back fast, quickly to the point we were before. So, importantly, for loads perpendicular to the grain, the effective number of axes should be taken as NEF equal to N. Okay? So if we had, for example, instead of the N in this way, but we have a shear connection, so if the connection was loaded this way, what would be the actual effective number in this case? The number of points. So there wouldn't be any reduction because they are all stressed perpendicular to the connection, perpendicular to the grain. For angles, you see between 0 and 90 degrees, between low and high direction, NEF may be determined by linear interpolation between A34 and A35. So, what does it mean? If you have, for example, suppose that your connection is subjected to both shear and axial force. So you have both of them. How do you solve the problem? You can do the vector. So basically you have a vector like this. So each connector is subjected to a force, shear force like this. Okay? So when calculating this relationship here, the NEF that we put inside here shall be determined first by considering the axial force. So would be this 3 times NEF that we calculated before. Then you calculate the shear, only the shear, you will get the whole N, and then you do a linear interpolation between, let's say, 0 and the angle of alpha that you find this way. So, okay? So basically for alpha equal to 0, it would be this value here. For alpha equal to 90, it would be this value here. If you are 45 degrees, it would be the actual average. Okay? If there is another value, you do the linear interpolation. It's clear how to do it? Because very often you will see, particularly when you are going to design your connection, you will get this kind of situation. You will get an angle which is neither 0 nor 90 degrees, somewhere in between. So we need to do this kind of you need to do this kind of procedure. Okay, now we said before the importance to have right washers or rondelle in Italiano. So, first of all, both holes in timber should have a diameter not more than 1 millimeter larger than the bolt. So, when we drill a hole in a timber member to insert a bolt, we need to have some clearance So if you need to use a bolt, let's say 20 millimeter bolt, it cannot be used in a hole which is 20 millimeter. It may be used, but then it's more complex to do it. Sometimes we do it bolted in tight-fitting hole, but in general we should have a clearance. So this clearance, or tolleranza in Italiano, shouldn't be more than 1 millimeter. So 20 millimeter bolt will go into a hole maximum 21 millimeter diameter, no more. Both holes in steel plates should have a diameter not more than 2 millimeter or 0.1 D, whichever is the greater, larger than the bolt diameter. So always the same 20 millimeter diameter bolt will go into a hole in the timber up to 21 millimeter and into a hole in the steel no more than 22 millimeter diameter. Okay? Washers with a side length or a diameter of at least 3D and a thickness of at least 0.3D should be used under the head and the nut. So the washer shall be first greater compared to the washer to be used for steel, and secondly thicker. You see the washer that I showed before, it's a thick washer. It's a thicker washer. So 3 diameter, so 20 millimeter diameter bolt should have a washer at least 60 millimeter diameter. And the thickness of at least 0.3 times 20 millimeter, which is so 0.3 times 20 is more or less 6 millimeter. So 6 millimeter thick, it's a significant thickness. In fact, if you touch the washer that I showed you before, it's quite significant. Bolts and lug screws should be tightened so that the members fit closely, and they should be retightened if necessary when the timber has reached equilibrium moisture content to assure that the load carrying capacity from the structure is maintained. So when we, you know that when we use bolts in steel connections, the idea is that those bolts should always be tightened. Well, will be tightened to ensure that there is a contact between the two members. They are tight fitting. In some cases, actually, you use friction bolts in steel. So you go to tighten purposely a lot the bolt in order to pre-stress the two plates together and to rely not on the bearing of the bolt, but on the friction between the plates. Okay? Now, in timber, we should tighten the bolts in order to ensure that the two members are tight fitted, they are not moving. The problem is that in timber, if we tighten too much, we have some problem. What kind of problem? First, we can indent the timber because we have a very strong material still bearing on a very soft surface. Because the bolt is bearing perpendicular to the grain in this case, if you think about like here. When I tighten the bolt, this one, you know, if I tighten the bolt, I stretch the bolt, so the shank is going to be in tension, and I apply a pressure here underneath the washer to the timber. This pressure this compression force is applied perpendicular to the grain, where the young modulo of timber is very low. So if I tighten too much the bolt, I keep on tightening, this bolt is going to indent the wood. So I shouldn't tighten too much. I should tighten the right amount, but not too much. This is the first thing. Second thing, what's happened? I tighten now the bolt. What's happened if I come back there after, for example, 1 year? Do I still have the bolt which is tightened? In general, it will be a little bit released. Why? Because timber is a creep material, not like steel. So being a creep, the material with creep, it tends to relax over time. Particularly critical would be the case where I use timber which is not dry. So I use timber which is still wet, not dry. I tighten the connection to the right value, and then I come back after 1 year. After 1 year, the timber is dry. When it dries, it reduces the length, particularly in the direction perpendicular to the grain. So when I come back, basically, I find that the bolt is loose. So there is no more contact between the members. So the regulation said that if we are planning to use timber which is not dry, which is going to dry over time, we should also plan to go back there and to retighten the bolts, because otherwise we have a bolt which is loose. Okay, it's clear? Obviously, due to this problem, in timber we cannot use this concept of friction, or that we use for the high strength bolt, in steel. Why? Because if we think about now, for example, pre-stressing now, so tightening along the bolt, we could get some friction now, but later on we will get no friction because the timber is going to creep. It's clear? So we can't really tighten too much the bolt to increase the friction. This doesn't work. It works maybe when you tighten the bolts, but then you come back after 1 month, you get nothing anymore. Okay? So keep in mind this is wrong. If you see, if you buy a bolt with a normal washer, this is not okay. You need to replace the normal washer with the larger washer like this. Okay, so this is more or less when you use bolt for timber. This is more or less the appearance of the bolt with a washer, not this. And then we can use double connection. Double connection is basically this one. It's a cylinder of steel, not threaded. This is the double, or spinotto, as we call in Italian. So we're talking about smooth shunt pins driven into closed fitting holes. In this case, of course, we need to drill the hole which is more or less the same diameter of the dowel, because otherwise this one is going to move and it's going to fall down. So this can be transfer loads from steel plates to timber, from timber to timber. It's very important to remember that this member here, of course, doesn't have any withdrawal resistance. So if you want to connect two members using only doubles, if those two members can fall apart, to avoid these two members fall apart, you always have to use at least 4 bolts to keep the two members together. Because at least the bolt with the head and the nuts can prevent the separation of the two members. Dowel alone cannot prevent any separation, any out-of-plane separation. So they should always be used together with at least 4 bolts to make sure that the system stays close together. Diameter is between 6 mm and 30 mm. In general, they behave like bolts. They can be designed like bolts. Those are spacing and edge and end distances for dowels, slightly different from the one we saw before, but not much difference. And then we have, that at the end can be designed like dowel, this kind of, you see, thin plate connection, so a plate which is inside, with this kind of self-drilling connectors like this, that have basically a point that can not only cut the wood, but they can also cut these aluminium plates that we find inside. Of course, this is very good because, as I said last time, when you do this kind of hidden connection, you never know what is exactly the hole. So from outside, of course, you know where is the hole of the plate. Then you put the plate inside. Then you can't see the hole anymore from outside. You know they should be there, but then when you start drilling, maybe you get, this one is not really perpendicular, slightly inclined, and then when you get there, you don't go through the hole anymore. Because I just remind you, this hole, if for example this one would be, let's say, 8 mm diameter, the hole cannot be 12 mm. The hole should be maximum, we said, 1 mm, so maximum 9 mm. So it's very difficult to get the hole when you drill from outside. Of course, it's easy if you have the plates outside, then you start from the hole and then you want the timber. But if you start from the timber, to get the right position of the hole is very complex. So much easier to have a connection that can drill also directly the plates inside the timber. So, and now we talk about a bit about the screw connections. So in the last, I would say, 20 years, in particular 10 years, we have done a lot of progress in the development of wood screws. So now we mostly use self-tapping screws. So screws that you see can be deployed up to a diameter of 14 mm without pre-drilling. So up to 14 mm, we just screw the screw inside without any pre-drilling, which is very convenient. So this is a photo of self-tapping screws. So those screws that can drill their way through the wood. In the screw we have a head and we have a shank. So the shank diameter usually, so this is the head, this is the shank. The shank diameter usually is smaller than the external thread diameter. So this is a threaded part. You can see that the external thread diameter is larger than the shank diameter. So the shank diameter should be somewhere in between the external and the internal, but not always, because for example here it's true, but here it is not, because as you can see that the shank diameter, well actually it's true actually, the shank diameter is in between the outer thread diameter and the inner core diameter. So the nominal screw diameter is generally the external thread diameter. So when we say that this is a screw 9 mm, it means that the diameter of this external thread is equal to 9 mm. Because strictly speaking, here we have three diameters. This one, external thread diameter, the shank, and the inner core, three diameters. So the nominal one is usually this one. So here we have some example. I can just perhaps now send to you. We have this self-perforating tip, which is a tip right in such a way that we can basically go inside the wood by reducing the friction with the wood and by making sure that this tip can cut its way through the wood without inducing too high stresses. Then we have a notch. So tip, this is the notch. You see here, this is the tip and this is the notch. Now I'm going to give it to you. This notch here, which is needed to cut the grain. The spacing of the thread. Of course, the spacing of the thread is important because if it is larger, it means that you need less turns to get the screw inside. But less turn, but more resistance from the wood. So we need to find out a halfway between the two. Then there is a cutter. This cutter is this element here. And this is used, it's needed in order to basically reduce again the friction. Then the ribs, and at the end here you have some a mark of the screw itself. So the screw can be fully threaded like this, or partially threaded like this. It can be also two parts, one part threaded, one part threaded, and one in between and unthreaded. Now, let's try to compare the behavior of nails versus screws. If nails and screws are subjected to axial load, you see something like this, you draw a blow. The nails are expected to have lower withdrawal resistance because they have a smooth shank, while instead, you see, the screw is expected to have larger withdrawal strength thanks to the thread withdrawal and the head penetration. Remember yesterday we were discussing about the two modes of failure of a nail that we can have also in the screw, of course. So one mode of failure is thread withdrawal for the screw, and the other one is head penetration in this case. So for the screw we have a much larger withdrawal resistance thanks to the threaded shank compared to the screw, compared to the nail. Instead, when we talk about lateral loads, so shear load, the nail have a lower withdrawal resistance, as we said before, which means that we have a reduced drop effect, up to 25% of the answer contribution. So this brings to reduced lateral load resistance. The screws, instead, they have a larger withdrawal resistance, which means an increased drop effect, up to 100% of the answer contribution. So the screws have also an increased lateral load resistance. So as you can see, thanks to the thread, screws and nails are better in terms of both withdrawal resistance and lateral resistance or shear resistance. Okay? Now, in terms of design of screw connection, there is a large variety of screws. So usually we have to take from the producer the values of characteristics in moment, tensile capacity, and withdrawal properties. So in general, the provision from the Euro codes, they are not enough to calculate all these properties. So these properties here must be taken directly from the producer. So the producer has to do some tests with some notified body and get some reports where it is written the actual properties that we should be using in design of the screw themselves. So the simplest way to design a screw connection is to extract the parameters, the mechanical parameters, such as yield moment, embedment strength, or withdrawal resistance, directly from the producer. So for example, if we use, let's say, rotoglass screws, which are produced here in Italy, you go on the internet, you download, there is a huge guideline with all the different products and all the properties. You can find from there, from the screw that you choose, directly the yield moment, embedment strength, or withdrawal resistance, and then you use those values directly into the Johansen equations. Particularly, you see the regulation said that this is taken from the Eurocode, that the effect of the threading part of the screw shall be taken into account in determining the load carrying capacity by using an effective diameter, dEF, when determining the yield moment capacity and the embedment strength of the threaded part. The outer thread diameter, D, shall be used to determine spacing, edge, and distances and the effective number of screws. So, for example, if you take the screws here, we said that there is D is the outer thread diameter. This is also the nominal diameter. So a screw which is 7 mm means that the outer thread diameter is 7 mm. So the screw load carrying capacity should be calculated using an effective diameter. Effective diameter is taken as, if this condition before is satisfied, is taken as 1.1 times the thread root diameter. So D1 is the thread root diameter, and the DEF, the effective diameter to calculate the screw load carrying capacity, is taken as 1.1 times D1. We can then use the Johansen equation with DEF instead of D, and with FH, so the characteristic embedding strength, and the yield, and the characteristic yield strength from the producer's data. So, The embedment strength of screws of nominal diameter up to 6 mm can be determined using the equation for non-preserved names. While instead for screws with diameter larger than 6 mm, the equation for bolts. When multiple screws are arranged in a row in a right direction, the ratio splitting means, as we've done before, a use of an effective number of screws less than n. So in the end, up to 6 mm diameter screw, we use this equation for the characteristic embedding strength. Instead, for screws larger than 6 mm, we use this equation taken from bolt design. For the embedding strength. So this is an example of a screw. Should be probably this one, very similar to this. So this is a kind of screw here. It's called VGZ connector. The nominal diameter 7 mm, which is the diameter of the outer diameter of the screw. Sorry, the outer diameter of the thread 7 mm. Then the head diameter is 9.5. The tip diameter is 4.6. The shank diameter, if there is no shank, so it should be here basically. Shank diameter is 5. And the pre-bore hole diameter, if you need to pre-drill, the pre-bore diameter should be 4 mm. From this table, you see the producer directly provides you with a characteristic yield moment, 14,000 Newton per millimeter. So we need the characteristic yield moment in the Johansen equation. We get also the characteristic extraction resistance parameter, FAXK, to determine the withdrawal resistance. We have the characteristic tensile strength, this way, to calculate the tensile strength of the fastener, and the characteristic yield strength, FYK. So, how do we use this parameter into the Johansen equation? First, we need to use the diameter. Which diameter do we use? The diameter in this case is the effective diameter. So it's 1.1 ds. But ds is the shank diameter, 5 mm. Okay? So. Then we need to know the embedding strength. For the embedding strength, since the diameter, the nominal diameter is larger than 6 mm, so 7 mm nominal diameter, we use the formula for bolts from the embedding strength. Here we use again this diameter here. Then we need to, the formula to use the characteristic yield moment, which is given in the table. Then we need to use the withdrawal resistance. For the withdrawal resistance, we have this equation taken from the Euro 5. So basically, the characteristic axial withdrawal resistance is given by this quantity here, where the characteristic axial strength is given by this other relationship, semi-empirical relationship. But again, D, in this case, is the nominal diameter. So in this case, 7 mm. So the characteristic extraction resistance parameter that we need in this formula here is provided here by the producer. And the tensile characteristic strength is given again inside the formula. Okay? So this is an example of how to use the parameters provided by the producer. But anyway, if you look again in this technical information provided by the producer, it will clearly explain how to use the Johansen equation with this parameter. Okay? Now, actually though, the screw. This is a very important case. As I said before, nowadays screws are mostly used inclined at an angle. Why is that? Because basically they have a very high withdrawal resistance thanks to the presence of the thread. In general, if we insert a screw inclined with respect to the grain, we will get that, strictly speaking, this screw will be subjected to both shear and axial force. So there is a combined effect of shearing and axial force. Since the screw is much stiffer in axial direction than in the shear direction, usually for the sake of simplicity, when calculating the load carrying capacity of an entire screw, we just ignore the shear resistance. So we just consider only the withdrawal resistance because it's much higher and much stiffer in axial direction than it is in the shear direction. So, now this you see is a possible connection. We have to connect one timber plate with another timber plate. Instead of using two screws perpendicular to the shear plate, we use one screw in one direction and one screw in the other direction. In this case, both screws are fully threaded. So, how do we design the screws? We take the shear force that we need to transfer and we decompose this force into a component, acting compression in one of the screw, and in the other one acting tension in the other screw. So if alpha is the angle, basically these two components will be one half F divided cos alpha, and the other one half F divided by cos alpha, where F is the force, the shear force. So the shear is decomposed into a component. Note that if you have a partially threaded screw, you can't arrange a screw in compression because this doesn't work. So, can you please now just check the difference between these two cases? So in this case, the screw in tension is fully loaded, it works in both parts. The screw in compression also can work because we have the thread. If you look at this other case here, so we use the screw which is partially thread, the one in tension can still work thanks to the head, which basically prevents the separation here. But the screw in compression cannot work because this part here is not threaded. Okay? So the head alone cannot transfer the compression force, can only resist the tension. So in this case, this is a wrong detail. We can use the partially threaded screw, but in this case we should only use the one in tension. Perhaps we should use two in tension. Okay? You can use the cross arrangement. So in this case, if you have only one, of course, you get twice as much as the axial force, the withdrawal force into the screw. Now this is a plot which shows you why it is better to use a screw at 45 degrees than a screw at 90 degrees. You see here? So this is the angle between the screw axis and the grain direction. If we start from 90 degrees, at 90 degrees of a screw which is perpendicular to the grain direction, you will get that in a screw, this will be the Johansen contribution, and this will be the rope effect. So already for 90 degrees, the rope effect will be larger than the Johansen contribution. If you remember, the regulation allows us to use up to 100% of the contribution. So we can use the whole rope effect. We can just double up this. But what's happening if instead we start inclining less the screw? Instead of 90 degrees, 45 degrees. Instead of at 45 degrees, we have a much lower Johansen contribution, because now the screw is inside, but a much higher rope effect. So in the end, at 45 degrees, you have a total load carrying capacity which is how many times? Let's see. 55 instead of here. No, sorry, instead of here. It's more than twice. So the load carrying capacity of an inclined screw is more than twice the load carrying capacity of a screw perpendicular to the shear plane. And also you see that at 45 degrees, the contribution of the Johansen contribution is just, let's say 5 out of 55 is just 1/11. So it's negligible. This means that when using inclined screws, like we said before, we can just neglect the Johansen contribution and just consider the calculation of the withdrawal strength. Now, if you look at this case, partial thread screw again, in this a partial thread screw used perpendicular to the shear plane. In this case, we have a concentration of stresses in this localized area, so at the interface with the wood. So we have that the screw is loaded and bending, and we have some embedment between the screw and the wood. So in this case, we could say that for shear loads, the shear resistance is proportional to the diameter. While instead, if you use an inclined screw, like here, we have that the stress is distributed along the entire surface, and the connector is mostly stressed axially. So in this case, the resistance is proportional to the thread length. So we can increase the resistance by simply increasing the length of the screw. The difference you see between using screws perpendicular to the grain and inclined screws is that by using screw perpendicular to the grain, we need more connector because the connection is much more flexible and is also more ductile. While instead by using inclined screws, we can use less screws because the screw is much stronger, and we have also less deformation. Again, partial thread screws perpendicular to the grain will give us very little rigidity and very good ductility, while instead total thread connectors will give us a lot of rigidity and very low ductility. You can see here experimental behavior. If you use inclined screws, you can get very stiff behavior, higher resistance, and then a brittle behavior. While instead if you use screws perpendicular to the shear plane, we get less stiffness and less strength, but higher ductility. So in the end, if you want, the conclusion is that if we need ductility, so if we need to design a dissipative connection in the earth area, we need to use the screws perpendicular to the shear plane. Instead, otherwise, if you don't need ductility, the best way is to use the screws inclined. So in this way, you get higher strength and higher stiffness. Here you can see some application example. We need to connect this beam to this secondary beam to this primary beam. We can use two inclined screws. One screw is subjected to tension, the other screw is subjected to compression, and so we can just decompose the shear force R into the two directions, parallel to the screws. Okay? To find out the withdrawal strength of both screws. Instead, on the right hand side, instead of using a crossover screw, so two inclined screws, we'll be using two screws but both inclined in the same direction. So here there was one in compression, this one in tension. Here instead we have two in tension. In this case, we have this equilibrium here. So we have the two screws subjected to tension, and then we have a compression force that develops between the primary beam and the secondary beam, and this is the equilibrium. So F is the compression force into the wood, and then we have F divided by 2 cos alpha like before in the two screws, both in tension. Now, in terms of resistance, of axial resistance of screws, what are the possible failure mechanisms? First failure mechanism is what we call withdrawal or extraction. So failure of the wood at the interface with the threads. How can we improve this strength here? By increasing the length. So the longer the screw, the higher this kind of resistance, okay? Because it all relies on the thread, on the length of the thread. Then, another possible failure mechanism, if for example, the screw is too long, if we do a screw with this diameter long 2 meters, what's happened is that probably the failure, the weaker link would be traction or head separation. So basically, the screw could break at the interface between the head and the screw itself. So we have basically failure in tension. Of course, if the screw is subjected to compression, then the failure is different. We don't have a splitting of the screw itself, but we have a buckling. So the screw could buckle, if you remember what we were discussing, when we were discussing the use of the screw, to strengthen the support region of a beam. We said we have to put some screws, and then those screws will be subjected to compression. We need to make sure that these screws don't buckle under compression. And then the other possibility is head penetration. So if the screw, if we have two members, and this member, those two members, they are moving apart, of course, if the head is too small, we can have this kind of problem with head penetration. So, the Eurocode says that for axially loaded screws, the following failure modes should be taken into account. Withdrawal failure of the threaded part of the screw, this one, we just mentioned. Tear-off failure of the screw head of screws used in combination with steel plates, and tear-off resistance of the screw head should be greater than the tensile strength of the screw. So basically this kind of possibility. So fracture of the screw just underneath the head. Pull-through failure of the screw head, this one. Tensile failure of the screw itself, this. Buckling failure of the screw when loaded in compression. And failure along the circle of a group of screws used in conjunction with steel plates. Block shear or plug shear. So basically, this is not a real case. This is, okay. If you screw it this way, you could have that you have a formation of this block here of wood which can separate from the other part of the wood. Okay? This is what is called here block shear or plug shear. There are also some limits in terms of distances, minimum distances. You can see from this block here. So A1 in this case is the inclined distance between the screw, 7 diameter. A2 is in the perpendicular direction, 5 diameter, and then this A1CG and A2CG. This distance is here. And then the formula. Also here we have semi-empirical formulations. You see that for connection with screw with diameter from 6 mm to 12 mm, we have this formula to calculate the characteristic axial strength of the screw. So NEF, effective number of screws, times FLXK, characteristic withdrawal strength perpendicular to the grain, times D, diameter, outer thread diameter, times LEF, LEF the penetration length of the threaded part. KD is a coefficient divided by the angle alpha, basically the inclination of the screw with respect to the grain. FAXK, characteristic withdrawal strength perpendicular to the grain, is given by this semi-empirical equation depending on the characteristic density of the wood. Okay, this formula is true if this ratio d1 over t is satisfied. If this ratio is not satisfied, we will use other formula. We have also reference to density, different value of density. Then we have this characteristic pull-through resistance of connection with axially loaded screws, given by this relationship here. Characteristic pull-through parameter of the screw, F, K, and so on. And then NEF effective number of screws. This is the characteristic tensile resistance of the connection. And NEF, as you see, is N to the power of 0.9, like for the names. So number effective of screw to the power of 0.9. If you have combined laterally and axially loaded screws, then we can use this quadratic interaction criterion to study the safety of the screw. Some example. This is VGZ. Of course, these screws come into a certain range of length. You can see here some different lengths that can be produced. Some devices to make sure that the screws are screwed at the right angle. So basically, we use this kind of devices to help the worker to screw the screw in the right direction, 45 degrees, not maybe 40 or 50 degrees. Here again, the mechanical properties. All these tables are provided by the producer. So you can find here, for example, the minimum distance for shear load, if the screw is inserted without a pre-bore hole, or if the screws are inserted with a pre-bore hole. Again, minimum distances for axial stresses, in this case, already calculated by the producer. And then here you have the case of a screw inserted with a 90 degrees angle with respect to the brain, and the case of a cross screw inserted with an angle alpha with respect to the brain. Here you have the formulations used for traction, for example, and you have here the values. So, for example, a 7mm screw with a length of 180 millimeter has an axial characteristic strength of 14.87 kilonewton. The traction is 15.40 kilonewton, and then you have a very different for partial thread withdrawal instead of total thread withdrawal, which is 6.56 kilonewton. Then sliding, the value of the strength. So all you need to do the design basically on these catalogs that are freely available on the internet from the producer. So if we do now a comparison between sliding, inclined screw versus shear, vertical, you can see that. So, for example, the 7mm diameter, as you increase the length of the screw, you increase significantly the resistance to sliding from 1.97 till 8.72. While instead, if you use the same screw used perpendicular to the shear plane, as you increase the length, you have an increase at the very beginning, but after, increasing the strength doesn't bring you an increase in shear resistance. Same for the longer screws. So, for the longer screws, the sliding resistance is much greater than the shear resistance. So the idea is that if we should use longer screws in order to get a much higher, much greater sliding resistance. Here is other tables to realize this cross connection using the screws. So shear connect with cross connectors here, you see maybe have the different formula, or the different value for the failure, for extraction and for instability. But of course, if you have two inclined screws, one screw is subjected to tension. So we need to check this screw versus extraction. The other one is subjected to compression. So we need to check the screw versus instability. So those are the two lines that we need to use. So this is a very simple example of use of this table. After that we can probably stop. So this is the example is to design a beam-to-beam joint loaded with a shear force of 10 kN at alternating extent in service class 2 for a medium-term flow duration class. So those are the geometrical properties: 320 by 140 the main beam, 260 by 80 for the secondary beam. And we want to use these inclined screws. So one couple of inclined screws or two couple of inclined screws. Relationship is FD, where FD is the shear force, the design shear force, so 10 kN on the whole connection, shall be less than or equal to RVD, so K mod times RBK divided by gamma n. So from this design inequality, I can calculate the characteristic minimum shear strength, which will be 1.3 if I use the Eurocode, for example. It will be 1.3 times 10 divided by 0.8, so 16.25 kN. So I need basically to get a configuration of screws, two screws, such that my capacity is at least 16.25. I go into the table, for example for the 7 mm, and find that if I use two screws, diameter 7 mm, 340 mm long, we get, you see here, one strength in extraction 17.4 and the resistance in compression 13.6. So, using a pair of screws of BB 7 mm diameter, 340 mm long, R1BK 17.4 is greater than 16.25 kN. However, you can see here, the traction, extraction 17.4 is greater than 16.25. However, instability is lower, 13.6. So we need to check, because the characteristic value in terms of instability will be lower. So we need to do the check for instability. For instability, since now we're talking about instability of a steel member, so it's no longer a timber design. We have a steel member, a screw, which may buckle. So strictly speaking, now we don't use anymore the Eurocode file to check the instability of the screw itself. It's not the instability of the screw and the timber together, it's instability of the screw. So we need to use the Eurocode 3. If you look at the Eurocode 3, the instability is checked in this way, by dividing the characteristic load by gamma n. But gamma n for instability is equal to 1 in the Eurocode 3. So it's 10 kN, the strength demand is 10 kN. And the strength capacity is 13.6 divided by 1, 13.6. So the check is satisfied. Okay? Now, the second thing we need to check are the distances, the minimum distances. So the catalog of the producer will give us also the minimum distances needed. You see this BHT minimum, for example, 130 mm. This should be checked with our condition. So BHT is the minimum, here is 140 mm. It is actually the value also then the producer is asking us to comply. So 140 millimeters is equal to 140 millimeters, so we are okay. Then we need to check the depth of the beam, 260 millimeters, again, we are fine, we have the limit. Then we need to check the breadth of the beam, minimum 67 millimeters, which is less than the actual breadth of the beam of 80 millimeters. So it means that we don't need to pre-bore the beam. Another option could have been to use a pair of screws LVZ 9 mm diameter, 280 mm long. So not only one pair, not only one pair of the 7 mm, but one pair of the larger diameter, but shorter. So if you go again, when is this? So one pair of 9 mm diameter, 280 meter long will give us 18.1 resistance, characteristic resistance to extraction, 22.8 to characteristic resistance to buckling. So 18.1 is greater than 16.25, so it's okay. In this case, we don't need to check the screw for instability because we see that the actual instability is higher than the other value equation. So we don't need to do the check. We need to check the distances. So the breadth of the beam, 115 millimeters, is less than the actual breadth, 140. Okay. The minimum depth of the beam is 220, less than the actual depth of 260. And then actually we find out that BNT minimum is 86 millimeters, which is greater than the B of our beam, which is 80 millimeters. So this means that we cannot avoid the pre-bore in this case. So we need to use a pre-bore hole, because with the pre-bore hole, the minimum breadth becomes 68 millimeters, which is less than 80 millimeters. So this second solution is for sure less convenient than the first, because we need to use two pairs, so 4 screws, and we need also to pre-bore. So it would be much more expensive to use four screws rather than 2 screws. Yes.
Prima numero di della senza.
Let's go to see. So this one, 86 millimeters. So I can avoid to pre-bore if I have a minimum breadth of at least 46 millimeters. Since in my case I have 80 millimeters, I cannot use this option. Before we were okay, if I remember well. Because you see, BNT minimum 67 millimeters. Our actually B is 80 millimeters. So it's fine, it was fine. Now they are asking a minimum distance which is greater than our actual distance. So we cannot do it. Okay?
It's convenient to be a limit or be a
Yes. So theoretically this is a perfect design. Because we are not doing,
but practically do something that change and be course maybe worker.
okay. No. This the regulation suppose that the worker should be able to keep those distances. So we don't need to ensure some further, I can say, tolerance to cover the errors of the worker. This is not needed. Okay? Okay, this was just a compression. So we can see this next week. Yeah, I think we can stop here because we are almost at the end. So next week, on Monday, we have a lecture together, 4 hours, and then on Wednesday and Thursday, you will have a lecture with Dr. Shomenta. It will start, the idea is that you have to finish the lecture about durability, you did several times ago, and then probably we are going to do one lecture, she's going to deliver one lecture about wind. Because if you remember, when we did the calculation of the wind for my work example, since that work example was done 3 years ago, 2 years ago, when there was the old regulation for construction Italian, with the, well, actually it was a new regulation with the old circolare. Now, last year, they changed the circolare. And the circolare has completely modified the way to calculate the wind. So now the calculation of the wind for a building has become a huge problem apparently. So some of your colleagues are doing now the design with the new circular. They found something like 90 load combinations according to the new circular because they are asking many more cases to do. So I think it's good now to avoid later on problems to have one lecture, 2 hours, what is needed to talk about wind. Even this is not, of course, it's not the main aim of this course, but at least that after not to get into trouble when you have to calculate the wind for your warehouse. If you are going to design a warehouse or a single story industrial building, so for sure you need to take into account the wind. So in these 2 hours, hopefully, you will clarify the application of the regulation. The proposal was actually, since the circular in some ways even more demanding than the Eurocode, we will do the lesson with the Eurocode 0, with the Eurocode 1, which is the one dealing with me. And then after, and I would say after that, I will have another week with me, we'll do some work example about design of connection, and then you'll be ready to start your project. In a way that hopefully you can complete the project by the end of the year. Okay? Any question about this further plan? No? Okay. So, thank you for your attention. We'll see you Monday at 3 o'clock.